We are going to have a look at some more past paper questions today, and we are going to have a look at some written ones this time for equilibrium. So basically, I'm going to start with this one. We've got atmospheric oxygen, that's O2, dissolves in the Earth's oceans, forming dissolved oxygen, O2 aqueous, which is essential for aquatic life. An equilibrium is established, and that's basically between the oxygen as a gas and the water it's dissolving in, and the dissolved oxygen. So first of all, what is meant by a reaction at equilibrium? Okay, this probably doesn't tell you the marks, but it's probably got 2 marks here. So the 2 marks that we would be wanting to say are going to be 1, the rate of the forward, and the reverse. So the rate of the forward reaction and the reverse reaction are equal. That's probably 1 mark. And then this one, we'd be wanting to say the concentrations of the products and reactants are equal. Not equal, constant. And we said that was because the products and reactants are always turning in to the other. So the products are always going back and doing the reverse reaction to make the reactants, but at the same time those reactants are going forward to make the products, and it's a reversible reaction. It's continuing on, and that's always happening. Let's try the second question of this, and it says what would happen to the concentration of dissolved oxygen if the temperature of the Earth's oceans increased? Well, what would happen is that this is an exothermic reaction. So this is the reaction here. So the forward reaction is exothermic. What would actually happen is a temperature increase would favour the endothermic reaction. So that means it would favour the reverse reaction here. So actually, as you can see, the dissolved oxygen is the forward reaction. So the concentration of dissolved oxygen would decrease. So you could almost swap that around to write it like this: O2 AQ and that is endothermic. This is favoured. This means that the O2, so the concentration of dissolved oxygen decreases. Okay, let's see if we can find another one to do. Let's try this one here, number 33. So what effect would the addition of ammonia solution have on the position of equilibrium in the above reaction? Well, ammonia is a base, okay, and that would react with the H+. This is a wee bit tricky, but it would do this. So ammonia NH3 plus H+, that would form NH4+. And if it does that, that means it's going to be taking away the hydrogen ion. That means that it would move the position of the equilibrium to the right. So H+ is removed. So the equilibrium moves to the right. that might be something you remember from National 5, the fact that ammonia was a base and it can react with acid. That is a wee bit tricky though. It's just another kind of one that you need to know. Okay, so let's try this one. So for this one, we've got like a balanced equation for a reaction at equilibrium, and they've got this kind of equation that we need to fill out. We've got this for here, and it basically tells you what A in brackets means. That just means the concentration, and the small a represents the number of moles. C and D are the products, A and B are the reactants. So we could do this for the Haber process reaction here. So K would be, and it's the products over the reactants. So we'll do NH3 in brackets, and then you're supposed to put the number of moles as a wee small number on top. So that's NH3 2 divided by, and then it's A and B, so that's the reactants. So we'll get nitrogen, which is N2, and we only have 1 mole of that, so you put 1 in there. Actually, if you had just written that on its own, because you're doing it to the power of 1, you don't actually have to put that number in there, but I'm just putting it in just to show you. And you won't go wrong if you do that. And we've also got this one, B, is going to be H2, but because that's got a 3 in front of it, you put a wee 3 up there, and that's the answer. Now, this is tricky. This isn't something you need to know. If they were going to ask you something like this in your exam, this is a problem-solving question, so you would need to be able to use information in the question to help you do the answer. There's enough information there for you to have done that. That's okay, it's just a wee bit tricky to get your head around. Second one, we're going to do what will happen to the position of equilibrium if the reaction is carried out over a catalyst. There is no effect. Catalysts do not affect the position of equilibrium. The position would not change. Okay, and for this one, it's talking about in industry, the reaction of nitrogen with hydrogen produce ammonia by the Haber process does not attain equilibrium. Give one feature of the operating conditions which leads to the Haber process not reaching equilibrium. Well, see, to be honest, this might not come up in the new hire anymore, but if you think back to when we looked at the chemical industry, we were talking about a continuous process. This is a continuous process, so as soon as that ammonia has been made, it's been taken away, so that means that you're never actually getting this state, like it's not a closed system, because it's always been kind of removed, so it's never actually given the chance to kind of go back to the nitrogen and hydrogen. So I would write for this one that it's a continuous process, or the Haber process. That's what I would say. It's continuous, so the reactants and products are not for long enough. Okay, there you go. That would probably never come up, but it's good kind of to know that if something like that did. So if it was talking about like a continuous process, something that was a big kind of industrial process, then to be honest, they're probably not going to be at equilibrium because it's a continuous process and the reactants are getting taken away as soon as they're made, so you can never actually get them turning back and having that equilibrium set up.